to FlippedHarber for Precalculus. In this video we're going to be talking about exponential growth and decay. Our objectives with this lesson are to be able to solve for exponential growth problems and to be able to solve for exponential decay problems. The outline for this video, it's pretty short. We'll talk about what exponential growth and decay equations look like. We'll be taking a look at a graph for each of those, and then we'll be working through an example that involves radioactive half-life. Now, exponential growth, we've seen a version of that when we talked about interest. We had continually compounding, we had compounding annually, compounding monthly, and stuff like that. That's an example of exponential growth. We're going to be looking at an equation that just uses e to some power as our exponential growth. So we see that in the red curve where it's actually starting at 1. The reason it's starting at 1, that's our beginning value, because I plugged in 1 for that a sub 0 value. The blue curve, we see exponential decay, not the inverse of exponential growth. The inverse would be a natural log. Exponential decay is a different type of function. Basically, if you look at it closely, the only difference is that there's a negative power on the e. So again, we see a starting value of 5, that is where it crosses the y-axis is 5, because I plugged in a 5 for that a sub 0 value. Now, let's take a look at an example, pretty typical of exponential decay and exponential growth. We're going to take a look at a radioactive decay example. Carbon-14 is a radioactive element that we use for dating artifacts, samples about how old a piece of wood is or how old a clay pot is. Carbon-14 is naturally occurring. It occurs at pretty much the same level for every living animal, every sample that we take. Carbon-14 starts out at the exact same amount, the exact same ratio, and then as it decays, that amount of carbon-14 goes down, so we can figure out how old the sample is based on how much percentage of carbon-14 is left. So carbon-14 has a half-life of 5,730 years. I'll explain what half-life is in a second. Our question is to determine how much is left of a 50-gram sample after 12,000 years. Now, the half-life of something, say the way that radioactive atoms decay is they decay in a very predictable exponential manner where every half-life they lose half of their sample. So if we started out with a sample that had 100 atoms in it, after 5,730 years, about 5,700 years, 50 of those atoms would be gone and 50 would still be remaining. After another half-life, about 5,700 years, another half would be gone. Now that doesn't mean that it's all gone. When we say a half-life, half of whatever's there is gone. So out of that 50 atoms, another 25 would be gone. So with this model, it's actually hard to determine how long before they are all gone. We can make some percentage statements, but every half-life means that the sample is cut in half, and then in half again, and then in half again. So it's getting smaller and smaller and smaller. But mathematically, we never say that it goes to 0. So we're going to use the exponential decay equation. Now, the big difference is the power here. So you got to make sure that you're using the one with a negative exponent. The math will actually take care of you if you screw this up, but try to start out with the right equation so that you don't screw it up, so you get the right answer. So our exponential decay equation, A stands for amount. So the amount that's left is equal to a sub 0, our starting amount. The reason we use a 0 is that 0 actually means time 0, 0 years. And then e to the negative kt. Now that k is a constant that we're going to need to solve for. And for every decay, every different radioactive isotope, we're going to have a different k value that we're going to have to figure out. It's well known for carbon-14, but hey, this is a math class. We've got to learn how to figure out what that is. Now really, that's going to be the first thing that we have to do in these problems is to solve for our K value. Now if I gave you problem after problem after problem of carbon-14, okay, you'd find it once and then you'd use it over and over and over again. It's not going to change. But You start out with a carbon-14 problem, you figure out what that K value is, and then you move on to a different radioactive isotope. You can't reuse that K value. It's going to be different for every radioactive isotope. After we find our K value, then we're actually going to try to figure out how much of this 50-gram sample is left after 12,000 years. So, starting with our equation, A equals A naught e to the negative kt, we plug in that time that we know. That half-life is 5,730 years. So that goes in for t into our power. So what we're going to solve for, the variable that we need to find, is the K value. We know that that's going to involve a natural log. We've solved for these variable powers before. But how are we going to deal with this whole A and A naught? Well, one way to deal with it is to just go ahead and plug in numbers. Plug in an amount that is half of our A naught. So if you want to just choose numbers like 50 is half of 100, that's perfectly fine. You can just do that. Another way to do it, and this is kind of more mathematically preferred because it shows that you have a deeper understanding of the algebra that's going on, we actually plug in 1/2 A naught for our A value, saying whatever that sample was, we've got half of it left. Now when we do that, those A naughts just cancel out. So we'll go ahead and head through this with that 1/2 A naught plugged in for A. Our A naughts will cancel, and that's going to give us our 1/2 equals our E value. Now that's the exact same number you'd get on the left side if you went 50 divided by 100. So you can always just plug in numbers if you want. Now I've got to solve for that K value, so I know that's going to involve a natural log. So the natural log of 1/2 is going to equal my power, so negative K times that 5,730 years. Dividing that negative 5,730 years over, I find out that my K value is approximately, okay, this is a lot of digits, 0.001209. Here's a tip for you. Take whatever that number is that you just solved for your K value, hit your store button on your calculator and store it as the variable K in your calculator. Then you're not going to have to type in all of these decimal numbers. So after you get this number, hit your store button, find your K, or even use your X. It really doesn't matter what letter you store it as, but store it into your calculator so you don't have to type all these digits. Now I figured out what my K value is, so now it's time to actually answer the question, how much of this 50-gram sample is left? So I go back to my original equation. Oh, I got that 1/2 there. That shouldn't be there, but it's right in this one. So I'm solving for my amount. It's equal to 50 grams. That's what I'm starting out with. E to my negative KT. Now I know what K is. This number is safe to use for carbon-14 pretty much forever. And I'm plugging in my 12,000 years. So I'm going to be able to plug this all into my calculator. And again, if you stored your K value in, you only have to hit the K times 12,000 in your power. You don't have to type all those decimal places. So once you plug it into your calculator, you get that your amount is 11.709. So what that is 11.709 grams of my original 50 grams are left over. All right, so that's it. This is all just an example of the exponential stuff and the logarithmic stuff we've been studying. These are just examples, and it's time for you to try some of these on your own. I'll see you in class, and I'll see you online.